Okay, this is a pretty complicated problem. This is going to be just a little bit longer than the normal video, so let's get right into it. Look what's going on here. We've got magnesium hydroxide, and we also have some magnesium fluoride, both considered possibility in the solution. This is a situation called simultaneous equilibrium. You're going to have two slightly soluble compounds that simultaneously exist in the solution, and you have to take care of those equilibriums at the same time. So what do I mean by that? I mean that if I have some magnesium hydroxide and it's a solid and it breaks up into magnesium ion and two hydroxides, that's in the presence of sodium fluoride, which is completely soluble, then that means that the fluoride will get together with the magnesium ion and it will form magnesium fluoride. Now we need to balance the equation. And so these two equilibriums are happening at the same time. And so this is a situation known as simultaneous equilibrium. Let's call this one reaction A and this one reaction B. So the KSP for this one is KSPA, and the KSP for this one is the reverse of KSPB, so it's 1 over KSPB. Go ahead and write the equilibrium expression for the forward reaction and reverse reaction and convince yourself that that's true. Now, we can combine these equations into one solitary equilibrium expression and say magnesium hydroxide plus 2F minus, and take a look at the magnesiums here. The magnesiums are going to cancel, and so I don't write those. We'll make a new simultaneous equilibrium with two OHs and one magnesium fluoride. Now, I can treat this like any other equilibrium with an ice table. Look what happens. These two solids are not going to be included in the equation. Now, it does say that I start out with some sodium fluoride, and sodium fluoride is completely soluble. So that means that I have 0.05 molar fluoride in the solution. We're going to say 0 hydroxide. Okay, so then let's go on with the ice table. Then what do we have here? We have minus x and, oh, let me back up, minus 2x and plus 2x. At equilibrium, this will be 0.05 minus 2x, and this one will be just 2x. Okay, well, what's the equilibrium constant for this new reaction, reaction C? Well, what happens when I add the two reactions together? When I add the two reactions together, I multiply the two equilibrium constants together. So KSP for the new simultaneous equilibrium equals the product of the two previous equilibrium constants. So that's KSPA divided by KSPB. And so that'll equal my new equilibrium expression, which will be products raised to their stoichiometric coefficients divided by the concentration of the reactants raised to their stoichiometric coefficients. And this is the expression that I end up with. Now I just have to put in the actual values for the equilibrium constants and go ahead and start working on solving the problem. The rest is just algebra. And what I end up with is 0.1376 for the new equilibrium constant. And that equals 2x quantity squared divided by 0.05 minus 2x quantity squared. And this is one of those situations where I have perfect squares, so I can take the square root of everything to simplify out of the quadratic form. And so I end up with 0.3709 equals 2x divided by 0.05 minus 2x. Okay, so the next thing I have to do then is I multiply both sides by the denominator on the right. So I get 0.37909 times 0.05 minus 2x, and that equals 2x. And so now I have to run through the parentheses, so that's 0.3709 times 0.05. I get 0.018545, and then multiply it by 2.3709 times 2, I get 0.7418x, and that equals 2x. Now I can go ahead and I can combine both sides that have x. So I get 0.018545 equals 2.7418x. Now dividing both sides by 2.7418, I get 0.00676. And remember that we're looking for the molar solubility. And remember that X is the molar solubility. So the molar solubility is 0.0068 molar. And that is the final answer. Okay.